Hello again. We're here for video number 3 in the series relating to K18 and amplifier measurements. In the last video we looked at differences between EVM measurements in K70 or the vector signal analyzer and K18, what is meant by raw EVM. We also looked at EVM in the frequency spectrum and some important topics around errors in EVM measurements when you have some non-linearity present. Today, I think we're going to talk a little about some of the basics of DPD, right, Florian?
Yes, we're going to do that. Thank you, Darren.
Great.
Hi, everyone. So in this third video, we will talk about the, let's say, basic things on DPD, basic DPD features in K18. As probably most of you do know, we have basically two different DPD modes in K18. The first and probably easier one being the polynomial DPD. And then what we have as a separate option, the K18D, is the direct DPD. Now let's start with the polynomial DPD. And I think we can state that today most of, at least the mobile handsets, use this easy format of DPD, which is simply applying a polynomial to whatever data you're transmitting. Definitely high power transmitters like base stations and also TV broadcasting stations, for example, they use much more sophisticated DPD methods. But let's stick with polynomial DPD for today, and I'll mention briefly what it can do, and we'll see what it cannot do. Right, so we're here in K18 again, and I have configured it to measure a single carrier signal again. It's actually the same signal we've been using last time, 100 megasymbol 64 QAM signal that's being sent out by an SMW into our demo amplifier and then being analyzed in K18. So as we can see here in the AM plot, the device under test is already compressing quite a bit. So the AM curve is on the upper end, definitely not linear anymore. And if we look at the phase plot, yeah, it's clearly non-linear up here. Right, so what is the first step in polynomial DPD? Polynomial DPD in K18 requires that we set up a model of the device under test. Many of you may have noticed that in the AM and AM plots, we always find the blue line, which is the model trace. Same in the AM. So basically what we're doing is we're modeling the AM and AM behavior of the device under test. And definitely the first thing before you do the polynomial DPD, you want to check that the blue line goes or is appropriate to whatever you're measuring. So basically it means the blue line should be, well, more or less in the middle of your measurement points. So the AM plot here looks okay. And I would say also the phase plot is okay. What we can already see on the left hand in the phase plot, the measured points, the blue dots, they are scattered quite a bit. So definitely the blue line is sort of, well, the model is not 100% accurate. What we can always do is adapt our modeling. So what parameters do we have? It's basically the polynomial order for AM and AM separately. It's the modeling level range. This is basically how many or what level range do we take into account for the modeling? Where do we do the curve fitting? And this is always from peak power X dB down. So if I put in 50 there, you can definitely see that the polynomial, at least for the phase, does something very strange. and we definitely don't want to have that. So I could go back to 30 or maybe even 20 or 25 is a good value there. We can see the model fits quite nicely here. Let's double check on the AM. Yep, I think that one looks good as well. So once we have made sure that we do have an appropriate model of the device under test, we can run another measurement. And then basically applying DPD in K18 is pretty much as easy as pressing the Update DPD tables on generator button and then activating it. And you can already see the result. The phase being, well, almost linear now. And the AM plot is not linear, and I'll tell you why in a minute. But before I'll tell you, or we discuss the results, I quickly want to share some more details on what's happening while you're pressing these buttons. So if we go into the DPD configuration in K18, we can see a few options here. First of all, you have the choice of either using the SMWs or signal generators real-time DPD option, which is the K541 on the SMW, and I believe we also have it on the SMBVB. Or if you don't have that option, you can always just generate a pre-distorted waveform file. However, the big advantage if you pre-distort the waveform is that you cannot simply exchange the reference waveform on the generator. You always have to redo the modeling. So it's definitely worth having a look at the real-time DPD feature on the generator because it gives you a lot more flexibility. And pretty much the other option that can make some difference is you can decide whether the generator should use a lookup table to pre-distort or really a polynomial. I have to point out here that the lookup table is also filled from the polynomial model that we have derived before. However, it's a lookup table, so it's fixed values. The DPD looks up the amplitude for each sample in the table and reads out from the table a correction amplitude and a correction phase. Whereas in the polynomial mode, it really puts the current sample into a mathematical formula, and that then uses whatever comes out of the formula.
We know that you mentioned about the a mobile would use DPD. What would a mobile typically use? Would it do a real mathematical model like the polynomial, or would it do a lookup table? So I guess my question really is, which one would be more appropriate to do the characterization?
It's actually a good question. I think the answer is both exist. I believe the lookup tables are more common. This is why we use that as the default setting, but it's definitely worth double checking that with your customer.
And also, just while you're on this screen, with the DPD method, if you switch between the generator option in K541 or you use the pre-distorted waveform file, you would expect to see the same results here, right?
Yeah, pretty much the same results. I mean, yeah. We have to keep in mind that the real-time DPD happens in the FPGA, but besides numerical accuracy, I don't expect any differences here. However, some people ask the same question about the shaping thing. Do you expect the same results? And here, clearly, the answer is sometimes you may get the same results, but you cannot per default expect the same results there. And I believe the easiest way to sort of find the reason why you don't get similar results there is simply to look at the curves on the generator. So let's quickly switch to the signal generator and look at the K541 option there. And as you might know, you always get these nice little graphs about the DPD curves there. So this is the curve for the lookup table. And basically you can see there's almost no correction here because the device on the test behaves linear there. And then our correction goes up to a certain maximum. And then it decreases again. And maybe let's take this one, the decrease, to explain some other behavior. So why is the AMAM correction decreasing from that maximum point? Well, the answer is easy. As you might know, K18 Dpd always or limits the maximum input power after Dpd to the same maximum input power we had before Dpd. So if we had a peak power of, say, 6.47 dBm before the Dpd, you can be sure that when Dpd is applied here, the peak power is still 6.47 dBm. We have two reasons for that. Reason A is because you want to protect the device on the test, meaning not destroy it by applying more input power. And reason two is we simply don't know what the device on the test does once you apply more than the previous peak input power, because we have not characterized it there. So this would require an iterative approach. And now, keeping in mind that the peak input power does not change when you compare before and after Dpd, let's look at the AM plot with Dpd active again. And what we can see is, well, a hard clipping up there. So I mentioned it does not look fully linear, but it has, well, almost a sharp edge up here. And that's simply the peak input power limitation we have just explained. Okay. So that was pretty much the polynomial Dpd in short. And before we move on to the direct Dpd, we should probably spend a minute and compare results before and after Dpd, because that's the main thing why we do Dpd. So I deactivate it, I do a measurement, we have around about 3.2% EVM, and I define some, well, arbitrary ACLR bandwidth and spacing here, and we measure something like 40 dB. Let's just copy the traces, then go back, apply the Dpd. You can see a decrease in EVM of, well, around about 0.8%. And if you look at the spectrum, we can also, at least close in, we can see a significant decrease. Right. In the next step, or the next question that often comes up is, can you sort of trade in EVM for better ACLR? And this is where a feature called crest factor reduction comes into the game, but we're going to talk about this in the next video. Let's stay with a basic Dpd for now. And as I said in the beginning, we not only want to talk about the polynomial Dpd, but we also want to have a quick look at the other method we have in K18, which is the direct Dpd. So coming from the default state where the polynomial Dpd is active, I just activate the Dpd or the direct Dpd here. And you'll see we no longer have the update Dpd button here, but a button called start direct Dpd. The main difference between the two methods is that the direct DPD is not based on a model, which in return means there is no way we can apply that in real time. All we are doing here is we are generating a pre-distorted waveform. And as I said, we don't apply any model, even though the modeling traces are still active here, just in case someone notices. But basically what we're doing here is we're comparing the reference signal, which is in the spectrum plot, the green one, with the measured waveform sample by sample. And for each sample, of course, the measured signal is scaled down with the measured gain. And for each sample, we compare the difference in amplitude and phase and correct that accordingly. Obviously, since our device is nonlinear and we want to compensate nonlinear effects, this is not going to improve the signal, or this is not going to provide an ideal DPD in the first pass. It has to be iterative. So, main difference is we don't model anything. As a result, we only get a pre-distorted waveform, no algorithm. And it can be run iteratively. Talking about the iterative approach here, I mentioned before, with the polynomial DPD, we cannot exceed the previous or the original peak input power because we simply don't know what the device under test is doing when you apply more input power. Since we do direct DPD iteratively, we can allow the DPD to apply more input power simply because, well, we don't know it in the first measurement, but we have an iterative approach. So if I simply increase the peak input power, I'll know from the consecutive measurement what the device under test is doing. The amount of allowable increase in input power is called gain expansion here. So the default setting is 0 dB, which is the same behavior as in polynomial DPD. But you can set it to 2 or 3 dB or whatever value you want to put in there, which means during the 10 iterations that we are doing in this case, the algorithm can increase the peak input power of that the generator is feeding to the device under test by 3 dB. And the other setting that we should quickly talk about is probably the DPD power linearity trade-off. Typically, or per default, this is set to 100%, which means try to keep the output power constant. And typically, this is what people want to do during DPD. The other extreme, 0%, means make sure the output is linear and don't look at the output power. Effectively, this will simply reduce the output power, the RMS output power, and this is typically not what people want to do. So probably 90% of all DPD cases will keep this setting at 100%. Right, so let's see what's happening when we do direct DPD on the signal. Okay, I'm in a single sweep mode to improve signal quality. All right, so we're done. And what we can see is the result. If you only look at EVM, the result is significantly better than before. And the reason for that is simply that direct DPD, since it does a sample by sample correction also compensates all memory effects. Or we could also speak about frequency response. So basically, when you do direct DPD, it includes frequency response correction and memory effects, which will mean there is no need to apply an additional equalizer after running direct DPD. Let's have a look at the spectrum. This looks interesting. Can you see that? ACLR here and here is really good, and then it goes up to, well, more or less what we had before. What's the reason for that? Well, it's simply our measurement bandwidth. Clearly, the direct DPD only works within the analysis bandwidth. So if we want to equalize the adjacent channels, we have to include them in the measurement bandwidth. And in this case, I think it would mean I have to set it to at least 350 megahertz. All right, let's give it another try and see if it does what I'm promising. You can see the EVM is now slightly worse than before, simply because we have more bandwidth and obviously more noise. But as a result, the ACLR is better over the entire adjacent channel as promised. And I think with that rough explanation of the differences between the two DPD modes, we'll conclude this video, and we'll keep the DPD enhanced features like IQ averaging and crest factor reduction for the next video.
I'm just trying to digest what you've gone through. I think there's quite a lot of points in that short video that will be interesting to AEs and to our customers. So yeah, let's conclude the video here and we'll wait till the next one. Thank you, Florian.